So we're going to do notes for 10-4 today, no problem. So just keep track of your notes. Oh, this stinks. I just bought this and it's, oh, maybe it just needs to warm up. Here we go, 10-4. I guess it just needs to warm up. Okay, so 10-4, we're going to talk about secants. I'm going to get a different marker. I don't like that this one's not working very well. There we go, secants and tangents. My Expo markers came in from Amazon, so now I'm back to using a whiteboard. All right, so just take notes. We'll do an assignment on this after your quiz next class. So just take these notes. Remember, keep questions off in your left-hand margin when they come up. This is going to be a little longer. I'm sorry. I'll try and go quickly, or you can watch it at twice the speed or something. It's going to be part vocab and then there's some procedures that I want you to follow. So first of all, we need a circle. We're going to talk some anatomy here of a circle. Oh, that's a terrible circle. It's my new marker. We're going to blame it on my markers. It has nothing to do with me. I can still do circles. It's just the markers that can't.
Sure, Mrs. Cardi.
Thank you, Mr. Cardi, for your confidence. Okay. Okay, so here we go. Draw a line through your circle, and we're going to put arrows on it, implying that it can go forever and ever and ever. And this line that goes through the circle and touches it in two places is called a secant line. And there is an internal part of the secant line and an external part of the secant line. So let's label this as the external part. And then the internal part is from here to here, or it's a secant segment, but you know it better as a chord. So a secant segment and a chord are the same thing. It's the internal part of a secant line. All right, so let's draw a line that only touches the circle in one spot. So the secant touches twice. This line here is called a tangent line, and it touches only one time. And yes, there is a relationship between tangent, when we were talking about right triangles, and this tangent line. We will not go into it in this class. That is definitely a pre-calculus lesson there to show how tangent and actually secant has something to do with it too. All right, so a tangent line, let's say you have a point here, this part right here would be called the tangent segment because it's part of the tangent line. Segment, there we go. This part where it touches the circle is called the point of tangency. That's my microwave. My husband needs to go get his lunch out of the microwave. It's going to beep a lot of times. All right, now if you have a radius, you know what? I'm going to stop the beeping. Here we go. There we go. It's going to stop now. Let's draw a radius then from the center to the point of tangency. All right. When that happens, when a radius touches a point of tangency, the tangent line and the radius are perpendicular. So we need to write that down. That is a theorem we need to know. So here we go. A tangent line is perpendicular to the radius drawn to the point of tangency. Okay, likewise, if we have a radius that is perpendicular so here we go. I'll just write it out. It makes a lot more sense. So if a line is perpendicular to a radius at the point not the center point, then it is tangent to the circle. tangent to the circle. So if you can remember, radius touching point of tangency, perpendicular. Okay, or radius is perpendicular to a line, that's the point of tangency. Okay, so let's talk about something called the two-tangent theorem. All right, here we go. The two-tangent theorem. This will apply when you have two tangent lines that touch or intersect outside of the circle. So here's a tangent line, and then we're going to draw another tangent line that's going to touch this tangent line outside of the circle. So the most logical place to draw would be like so. So here's where they touch outside of the circle. This is the point of tangency for both of them. Let's call this X and Y, and we'll call this point P where they touch. Okay, if they the two-tangent theorem says if two tangents are drawn, two tangents are drawn to a circle from an exterior point, then those segments are congruent. So in this case, XP is congruent to YP. And the way you could prove it is, let's say you were asked to prove it. I don't know when you would be asked to prove it. A quiz, possibly, a test. You can draw in some lines, some radii, and then you can draw a line over here. And remember, perpendicular, and then we have congruent by the reflexive property and congruent because they're radii, so, and right triangles, so HL, these are congruent triangles, therefore CPCTC, that works. All right, but you can just jump to this now because we have the two-tangent theorem. Oh, that's my kitty cat. He wants me to go outside with him. Alrighty, let's draw two circles. Oh, they can be the same size or different size, but they're only going to touch one time. And one circle, and they're on the outsides. They're going to touch like so. And then remember, each circle has a center. So this point right here is called the point of tangency again because they're only touching in one spot. But these circles are externally tangent. Externally tangent. And the line that joins their centers goes through the point of tangency. That will always happen. Kind of cool, huh? All right, let's draw two other circles, but this time they're going to be inside. One's going to be inside the other, and their point of tangency is right there. And here's the center of each. These guys are called internally tangent. And if you draw a line connecting the centers, guess what? The point of tangency is also included there. Kind of cool. All right, we're still doing vocab building. So let's go ahead and we shall talk a little bit more. Let's do two circles. I made one of mine a little bigger than the other. Doesn't really matter. And here's their centers. We'll call them P and Q. And so the line PQ is called the line of centers because it connects the centers. All right, now we're going to draw a tangent line, but it's going to be tangent to both. So here's my tangent line, and we'll call this X and this Y. So the line XY is called the common internal tangent. It's the common internal tangent because it crosses the line of centers. All right, and then one more tangent line. Let's go from here to here. And we'll call this point, I like A better because I like to read from left to right. We'll call this A and this B. So the line AB is called the common, I'm sure you could probably guess it at this point, external tangent. It doesn't cross the line of centers. The only one that does is the common internal tangent. Okay, that concludes our vocab building. So let's do some examples of when we would use this stuff or why we need to know it. So here we go. Here's an example. And we need a circle over here. It's going to be a little proof and another circle right here. And this is circle P, this is circle Q. And we'll draw a line like so, and like so, and like so. And this is us, X, Y, T. And we are given that XY is a common internal tangent to circle P and circle Q at X and Y, points X and Y, sorry. And then we know that X, we're also given that XS is tangent to circle P at S, and YT is tangent to circle Q at T. We're going to prove that XS is congruent to YT. All right. So let's take a look at this guy. Well, we can talk about, let's just take a look at circle P. We have a tangent here, a tangent line, pardon me, and a tangent line. So we can use the two tangent theorem to say that SX is congruent to XY. So by the two tangent theorem, SX is congruent to XY. Well, wait a minute. If we look at circle Q, we also can apply the two tangent theorem, right? And we can say that XY is congruent to TY. So I'm just going to add on to this statement because it's the same reason. And XY is congruent to TY. Oh, well, we got this in the bag now. Therefore, by the transitive property, XS is congruent to YT. Great, that was easy peasy. All right, let's do a little bitty example down here. Here's your circle, center, radius, tangent line. This is circle O. You're going to need to find OP, and we're given that the radius is 8 and TP is 6. Get it, TP? It's just an appropriate joke for this time in our lives. Okay, so here we go. What kind of triangle is this? Don't open your mouth until you've thought for a couple seconds, okay? We have a tangent line meeting a radius. Okay, so it's a right triangle. So we can say 6 squared plus 8 squared equals OP squared. Or some of you are like, Ms. Carty, this is a family. It's the 3, 4, 5 family. So 6, 8, OP is 10. All right. That was a little bitty example. That was kind of fun. Let's do some more stuff. Let me get my fancy eraser. See? It's super fancy. Don't worry, it was clean. I never used it. All right, here we go. We're going to do the common tangent procedures now. Common tangent procedures. I have to show you my cat because this is what he does all day long. And he's taking my couch. Can you see him? He's taking my couch and making a dent because he sits in the same spot all day, every day. That's Joe. Okay, back to math. Sorry, I had to show you that. All right. There we go. Okay, common tangent procedures. Everybody get that written down? All right. So here we go, common tangent procedures. We're going to need this for, now we're going to write an example below so you can kind of get a gist of when you would use this. So a circle with radius of 8 is externally tangent to a circle with radius 18. Find the length of the common internal tangent. Find the length of the common internal tangent. All right, we're going to need a picture. So we have a radius of 8 and a radius of 18, so that means one larger circle, one smaller circle. And the circles are going to be tangent, externally tangent. So remember that looks like that. Center, center. Okay, here's our procedure. Step 1. Draw a segment joining the centers. Draw a segment joining centers. So here we go. Which is funny, let's draw, this is going to be 8, right? That radius is 8 and this radius is 18. All right, step 2. Draw radii to the points of contact. Oh shoot, we forgot to draw in our external tangent. Here, let's do that. There's our external tangent. Okay. Oh, I messed that up. Common, this should be external, not internal. No wonder you're like, what's going on? Common external tangent. I'm so sorry. Yeah, change that to external. It's not internal. My bad. Okay. Draw radii to the points of contact. Or we're going to say tangency because that makes more sense to us and it sounds fancier. Draw radii to the points of tangency. So here we're going to draw radius. Here's one point of tangency. Here's the other one. So just draw radii in. There we go. All right, step 3. From the center of the smaller circle, draw a line parallel to the common tangent. From the center of the smaller circle, draw a line parallel to the common tangent. This is the hardest part of the whole thing. So from the center of the smaller circle, draw a line that is parallel to the common tangent. Here's our common external tangent. We're going to draw a line parallel. Ready? Here we go. Parallel. Done. Okay. When you've done this, step 4, you are going to notice some things now. Notice that a rectangle, right? Rectangle because right angle, parallel lines, so right angle, right angle. So notice that a rectangle and a right triangle are formed. All right, here's our right triangle over here. Rectangle, right triangle. Step 5, last step. Use Pythagorean theorem. I know, kitty. Pythagorean theorem and properties, we'll say props, of rectangles. Okay, what is the radius of the smaller circle again? 8. What is this line then? Remember, it's a rectangle, so this is 8 from here to here. What's the radius of the large rectangle, though? This whole thing is 18, so that makes this piece from here to here 10. All right, we're gonna dong 4 because it's 4 o'clock. All right, so we've got a right triangle. I'm gonna redraw it a little bit. I'm gonna draw it outside of the circle so you can see it maybe a little bit better. Here's your right angle. This is 10. This hypotenuse is 18 and 8, so 26. It would be great to find this piece because this piece is the same measure as our common external tangent. We'll call it x. So this is x. And you can use Pythagorean theorem, 26 squared equals 10 squared plus x squared. Or you can go, hey, it's a family. It's a 5, 12, 13 family. So x would equal 24 because that's the 12 side of the 5, 12, 13. So x equals 12. Your common external tangent is 12. All right, if you feel like you need some practice, which I highly recommend it, try problems 13 and 14, and then maybe press start again on the notes just to get some practice before moving on to our last type of problem. And I will erase while you're turning it off so that when you come back you don't miss anything, I hope. All right, our last type of problem is called a walk-around problem. Walk-around problem. You're going to walk around the circle. So you're going to have a circle, and then there's going to be a quadrilateral that is circumscribed, circum meaning around, scribed meaning drawn. So it's drawn around the circle. It's just a quadrilateral, nothing fancy, no rectangles or squares, just a quadrilateral. Pardon me, and we'll call it A, B, C, and D. And let's say that you're given that AB is 10, BC is 15, and AD is 18, because I draw to scale every time. Okay, your job is going to be to find CD. All right, so we're going to walk around the problem. So you're going to start with one of the sides that you know. So we know AB, and you're going to take a piece of it. So from the point of tangency out to the corner, we're going to call that x. And we're going to apply the two tangent theorem. So if this is x, then B to the point of tangency is also x because they're congruent, two tangent theorem. Okay, the point of tangency to A would then be 10 minus x. And the point of tangency to C would be 15 minus x. Two tangent theorem says that if this is 10 minus x, then this is going to be 10 minus x. And if this is 15 minus x, then this will be 15 minus x. Okay. Now here's the tricky part. If this is 10 minus x, then what is the point of tangency to D? And I'm not going to have enough room. I'm going to draw a little arrow here. Well, the whole side is 18 minus this segment here, which is 10 minus x. That's the hardest part right there. Well, if this guy is 18 minus 10 minus x, then this piece from D to the point of tangent C is also going to be 18 minus the quantity 10 minus x. So we've walked around the whole problem. Still don't know CD, right? Well, let's go ahead and look. CD will equal this piece from C to the point of tangent C plus this piece from the point of tangent C to D. So 15 minus x plus 18 minus the quantity 10 minus x. Okay, let's do our algebra now. Geometry part is done. Let's do algebra. So 15 minus x plus 18, distribute the negative sign. And look what happens to our x's. It's a knockout. Boom, boom. So I've got 15 plus 18 minus 10, so 23 is CD. I love walk around problems. For whatever reason, I find them extremely gratifying. Okay, try number 10 as a walk around problem. All right, and I will see you in our Zoom session. Bye.